This is a unit on model selection, but we're going to slide into that topic maybe a little bit sideways by first looking back at our familiar distribution of the lengths of the exons in the human genome. What you say, haven't we done every possible thing with this little toy data set that we can possibly do? So let's review what we've done. We looked at the data and we saw that maybe it looks like two centrally peaked distributions, one here and then a broader one somewhat to the right here. And so on this binned data, we did a chi-square model with two Gaussians. That's equivalent to a weighted nonlinear least squares model. And it's a maximum likelihood estimate if the experimental errors are normal, which isn't quite true here because we have Poisson counts, but it is also true in the central limit theorem limit, and that is very true for this data because you'll see the numbers of counts in these bins are big numbers going up to 3 times 10 to the 4 up here. So we did that in segment 25. We came back to this data in segment 28 when we were learning about Gaussian mixture models, and we did a two-component Gaussian mixture model to this. What was different here is we didn't need to bin the data, and it's always good to avoid arbitrary binning on data when you can. We're going to see in just a second that when your data is sparse, it's quite essential to avoid this arbitrary binning. Well, Gaussian mixture models are also maximum likelihood estimates, but it's a particular model that's very specific in having Gaussian components. It doesn't allow for other shapes for these centrally peaked components out here. One of our reasons for trying this practice data set on a GMM was to illustrate EM methods, expectation maximization methods, which are often computationally efficient for doing MLE problems that would otherwise be computationally intractable. But for this particular data set, the problem was that with two components, it gave a terrible fit to the data. And that's in segment 28 if you want to go back and review it. Well, the problem was, as we'll see, that the assumption that these components are Gaussian is just too strict for this data set. So what we haven't done yet is a maximum likelihood estimate on unbinned data, but for a model more general than Gaussian components. This requires general nonlinear optimization. That's okay. We might get into trouble on it, or it might just go through smoothly. And for simple models or small data sets, this is a very reasonable approach. And it will, by the way, lead us to the topic of this segment, the model selection issue. For complicated models, looking at this will also prepare us for a later segment in this series on Markov chain Monte Carlo, a very important topic. So as always, we focus on what is the probability of the data given the model parameters here. For a frequentist, this is the likelihood of the parameters. As we know, for a Bayesian, it's the probability of the parameters, but there's some assumption of a uniform prior that also is made then. So the maximum likelihood estimate is the value of the parameters which maximizes argmax over theta, the probability of the data given those parameters. Now I want to actually try this on a data set which you're less tempted to just bin, and so I'm going to make this data set sparser. I'm going to pick just 600 random exons from the several tens of thousands in the complete data set, and I'm doing that here. And I'm here showing you then what the data set is we're actually going to use. Well, I'm showing it here to you binned so that you can see it as a histogram. Notice that the number of counts in each bin is now something between 0 and 100, whereas before it went up to 30,000. And correspondingly, these components look a little bit rattier, especially this one out here, where we're seeing the fluctuations in the counts here. And as before, we're going to be interested in not just the model itself, but an actual number that comes out of the model. What is the ratio of the areas of the main component here to the outlier component over here? Now the data points are assumed to be independent. So the likelihood of the model is the product of the model probabilities over the data points. A little hint here is that likelihood, that probability, will almost always underflow when you have any number of data points, because you keep multiplying numbers somewhat less than 1, and eventually you have so many data points that it underflows on the machine. So it's common to do all the calculations using the log of the likelihood, and we'll see that this is also useful for estimating errors. So what does the log likelihood function look like? Here it is as a MATLAB function. L is the log of the likelihood, and it's going to depend on the parameters of the model, C, and on the vector of points, the data set, the vector of 600 exon lengths. So we want to evaluate the product of the probability of these x's in the model, which is the sum of two components. Well, here's the first component, and its probability density function is proportional to this exponential, in which you see the usual location of the mean and standard deviation, and I've normalized its height to 1. You'll see why. It doesn't matter what the normalization is. The second component, it does matter. I have to tell you what is the ratio of its peak to the peak of the first component. So that's a parameter. Then there's a parameter C4, which is its center, and a parameter C5, which is its standard deviation. So the model itself is the sum of these two functions, but now properly normalized. So I simply take the sum. By the way, these p's are vectors because they've been evaluated for each value of the vector x. So I add these two p's. That's the sum of two Gaussians. And now I have to make their area come out 1, or at least come out a constant, because it doesn't really matter if that constant is 1. Its log would simply be an additive number, an additive constant in the log likelihood. But here is something proportional to the area of the first distribution, that is to say its height of 1 and its width of C component 2. And here's the area of the second piece. Its height is C3 and its width is C5. Then finally, the likelihood, or the log likelihood, is simply the sum of minus the log of all of the components in this vector P. Okay, we've defined a likelihood function, in this case for two Gaussians, and to actually do the fit requires only these 3 lines of MATLAB. We choose some starting values for the fit, some guessed values, so I'm guessing here center and width of the first component, center and width of the second component, and a ratio of the areas, the parameter C3. And then we simply call MATLAB's general search for a minimum function with our function, now written as an anonymous function, as a function of the parameters only, that is to say, locking in the true data set x that we have here. And we give it a starting position, and it will simply return the values of the parameters at the minimum as best it can find it. Now this is not always as easy as it looks, because there is no such thing as a general minimizer that works on all functions. You can get hung up on local extrema. You can choose the wrong minimization method. Somewhere buried in this fmin search is some decision on what minimization method is going to be used. You can have a starting guess that's too far from the minimum that you're trying to reach. That's why it's always good to choose a starting guess to be closest to the previous successful parameter set, especially if you're doing a sequence of problems or if you've been playing around with the problem for a while. Anyway, in this case it works just fine, and we get these values for the parameters of the maximum likelihood estimate. We're interested in the ratio of the two areas, and those two areas, well, you see them as the two separate terms up here, are the ratio of the fitted parameter 2 to the product of the fitted parameter 3 times the fitted parameter 5. And that comes out 1.6396. Well, we don't expect that when we did this problem before in segment 25, we got a ratio of the areas that was 6.3, and we did a whole error analysis in a couple of different ways, and we got the error on that 6.3 as being plus or minus 0.1. And that's completely inconsistent with this ratio of areas 1.6396. Now I want to remind you that it's not exactly the same data. This used all the data. This used only a random sample of 600 data points. So we might expect to get a much poorer estimate. But if we went back up here and did our error estimation thing, for example using the Hessian second derivative matrix, that wouldn't help. It would come out, it turns out, with an error of only about 0.3 on this number. So that's not what the problem is. The problem is not with the maximum likelihood estimate or with the techniques that we use to find that maximum likelihood estimate. The problem is actually with our model of two Gaussians. And it's time to face up to the truth about this data. This particular data really isn't a mixture of Gaussians. Those biological exon lengths don't know how to make a tail that falls off as rapidly as a Gaussian tail falls off. This is a mixture of heavy-tailed distributions. Now, why were we able to get around that before? Well, in the previous segments we had lots of data, and if you go back you'll see we did a bunch of sort of special little tricks. We trimmed the tails a bit. Okay, and then when we did the Gaussian mixture model, you'll recall that two components didn't fit very well at all. We added a third component, and that gave a much better fit. And what was going on there? Well, that broad third component wasn't really physical, but what the fit was using it for is to take care of the broad tails of the two other components and then kind of free up their degrees of freedom to give a better fit to the point in the middle. But it was a kludge. What we actually need to do is add a new parameter to our model to take care of the tails. Now this ought to worry you just a little bit. Aren't we just shopping for a good answer? Are we overfitting? The famous quote by Fermi, although he attributed it to von Neumann, is that with 4 parameters I can fit an elephant, and with 5 I can make him wiggle his trunk. And maybe we're just making this data set wiggle its trunk in a non-physical way. But let's try it. Let's try a maximum likelihood estimate on a heavy-tailed model, and we'll make our model heavy-tailed by using student t-distributions instead of Gaussians. And we will limit it to 2 components, because that's what intuitively we keep seeing in the data. So this adds a new parameter, nu, which is the index in the student t-distribution, to the model. And we're going to have to come back and ask, is this parameter justified? And that's exactly the problem of model selection. How far can you go in adding parameters to a model until you get a good fit? Now notice that our new model contains the old Gaussian model as a special case, since student's t-distribution goes over to a Gaussian in the limit of this parameter nu goes to infinity. In fact, let's remind ourselves what some student t-distributions look like. Here are student t-distributions for a range of parameters nu. Up here at the top in red is the normal distribution. That's the limit of nu equals infinity. Then we come down to some large values here. The purple value here is nu equal to 4. And we come down here to, I think the bottom one is nu equals 1. And you'll see that what we really care about is not so much the shape in the center. We care about that these have different power laws in how the tails fall off, and that will allow us to better fit the data. So here's the calculation using student t's instead of 2 Gaussians. This should look familiar. This function L up here has exactly the form that it had previously. The only difference is I've changed its name to 2 students log likelihood, and instead of a normal distribution in here that we had written out explicitly with the exponential, we simply call the MATLAB function t-distribution probability density function, tPDF. And we call it twice here for the 2 components. Otherwise that's the same. And then here's the ratio that we're interested in, that we thought was a value more like 6, but that was coming out something like 1.3. Well, here I've done the fit using the fminSearch function for 3 different fixed values of this student parameter new. When I do it with a value of 10, that's a pretty large value. That's something on its way to becoming a Gaussian. I get a ratio of these components, of the areas of the components, 3. Now when I lower the new value to 4 here, the ratio goes up. It goes up to 8, which is even larger than that value 6 that we saw before. And when I lower it even further with the new parameter 2, we get a ratio of errors of 10.77. So this is a little confusing. It looks like we can get any ratio we want by assuming something about the tails. That means that this is a real parameter that we have to fit for. We can't just guess what that parameter is going to be and expect to get any reasonable answer. So here we're going to fit for the parameter also. We're going to add a new component to the parameter vector c sub 6, which is the index new in this tpdf function. Now when we do the fminSearch, here we get values for the 2 components, and here we get out the best fitted value for the student new parameter, 4.3 approximately. And here we get out the best value in this model of the ratio of the 2 areas, 8.4 approximately. So now we arrive at the model selection question. Should we really add new as a model parameter? Adding it makes the model much better. So the question of model selection isn't one of does the new parameter make the model better? A new parameter always will make the model fit better. But how much better does the fit become? How much does the log likelihood decrease? And you might have thought that model selection was a settled issue in statistics, because it sounds like it's just some kind of statistical calculation that there ought to be a theorem about. Well, it turns out it's not a settled issue at all. Let me kind of indicate why with a couple of examples. So here's a very idealized example. Suppose you start a model with q parameters, and what makes this idealized is I'm going to suppose that that is in fact the correct model. You need exactly q parameters to fit the data. So in chi-square fitting, its chi-square is going to have n minus q degrees of freedom, where n is the number of data points, and therefore that chi-squared is going to come out with a typical value of n minus q, the number of degrees of freedom, and plus or minus the width of the chi-square distribution with that number of degrees of freedom, which is a standard deviation of twice n minus q. Now suppose I add an additional r unnecessary parameters. Well, this is still a correct model. The fact that the parameters are unnecessary doesn't spoil the model, because I have the q correct parameters still in the model. But chi-square is going to decrease, because now the number of degrees of freedom is n minus q minus r. In other words, chi-squared is going to decrease by 1 for each added parameter. But this is overfitting. Since these r extra parameters are unnecessary, they're not really fitting the underlying signal. They're kind of fitting the randomness in the noise. And that does decrease the chi-squared. But if we went off and found a new data set, we would not find that these same best values of r did us any good at all, because we'd have a different set of noise in the data, and the r parameters fitted from the previous data would simply not be applicable. And that's what overfitting is about. Now what does this suggest about model fitting? It suggests that it's okay to add parameters, but only if each time you add a parameter you get a change in the chi-squared that's much bigger than 1, that's not just this automatically decreasing by 1 for each time you add an unnecessary parameter. So that sounds pretty good as a criterion for model selection. But the trouble is, in real life, you're not starting with a true model. You don't know when you've hit the true model. So let's take an example conceptually where you have a model again with Q parameters, but it fits really badly and it's thus incorrect. So as we start adding parameters and decreasing chi-squared, we're rightly expecting to look at how is the model failing as guidance for what kind of new parameters we should add. Do we see that there's a third component, so we should add a new Gaussian? Do we see that the tails are wrong, so that we should do what we've been doing with students' t-distribution? Well, it's not surprising when you do that kind of thing that you can get chi-squared greater than 1, I should say change in chi-squared greater than 1, even when you're overfitting and exploiting the particular randomness. So your model's getting better and chi-squared is going down by more than 1 each time, but you can still fool yourself by overfitting because all of your models might be incorrect, just getting closer and closer to properties of both the real data and its noise. The real problem here is almost a philosophical problem. It's that we don't have a theory of what is the space of models, or a theory of why we think that within that space of models, simple models are more likely to be correct than complicated models. So people have developed different model selection schemes that make different trade-offs between goodness of fit and model simplicity, amounting to different partial, half-baked theories of what does this space of models and simplicity look like. One such scheme is called the AIC information criterion, AIC. And that simply says that the log likelihood should decrease by more than 1 unit of log if you're going to accept a new parameter. Now recall that log likelihood delta L is a half of delta chi-squared. So the delta chi-squared is 2 delta L, and therefore AIC says accept a parameter if chi-squared decreases by 2 or more. Well, competing with AIC is something called BIC, the Bayes information criterion. And that says that the change that you should accept depends weakly on the amount of data you have. There's a sense in which if you have more data, it may be easier to overfit, and therefore you should require a more stringent criterion. So the BIC says you should accept a new parameter if the change in log likelihood is greater than a half log n, where n is the number of data points. For our example with 600 data points, this would come out 3.2, which is therefore more stringent than this value of 1. Now, people don't just make this up. There are theorems behind each of these information criteria, behind AIC and BIC, but the theorems are only as good as their assumptions. If you Google for AIC, BIC, you'll find a bunch of web pages with all manner of unconvincing, in my humble opinion, explanations about what those assumptions should be, and then grinding through the theorems that lead to the AIC or respectively BIC criterion. Also note that this whole enterprise is a little bit subjective because it often depends on, in our example, what value of nu you started with as the natural value. We started with nu equals infinity, Gaussian, as the natural value, and we're going to look for decreases in chi-squared from that. But what if we lived on a planet where everybody worshipped students' distribution with parameter 4? Well, then that would be the natural value, and then when we add nu as a parameter, we might get a much smaller change in delta L, and therefore we might not accept it as a parameter. So again, a little bit of subjectivity here. Now there are alternative approaches to AIC and BIC. I'm going to put 2 of them in the small amount of space remaining on this slide, so this is probably something that you should follow closely. In machine learning, people tend to use purely empirical approaches to test for overfitting as they add parameters. So these are things like bootstrap resampling, leave one out, k-fold cross-validation, and so forth. This is a really good idea. Even if you're using AIC or BIC as your kind of first indicators of how many parameters you should have, it's a really good idea to do some empirical check on your data set to see that you're not overfitting. Now, a more modern alternative approach to model selection is something that we can loosely call large Bayesian models with lots of parameters. The idea here is, let's just not worry about the number of parameters. Add all the parameters you think you need so that you may well be overfitting. But the defense against this is going to be that we're going to calculate full posterior Bayesian distributions of all these parameters. And then we're going to just marginalize, in the usual Bayesian sense, over all of these parameters that are probably unnecessary that we don't care about anyway. So this Bayesian viewpoint simply puts less emphasis on goodness of fit and more emphasis on let's only ask the questions that we really want to ask about the parameters that we really think are important. There are in fact ways to impose simplicity constraints in these large Bayesian models, kind of by hand. In other words, if you have a parameter that you think probably just has a value 0, but that possibly should be a free parameter, then put as a prior a probability of 0.8 that it is masked at 0. In other words, a delta function is 0, and then give it a broad prior distribution in the remaining 0.2. The computational technique that lets us do this kind of calculation is Markov chain Monte Carlo, a very important technique in modern Bayesian statistics, and we'll come to that in later segments. So finally, back to our student T example. How does the log likelihood change with that exon data when we allow nu to vary? And here I've plotted log likelihood as a function of nu for the best fitting parameters for each value of nu. Now it turns out we started over here with Gaussian having a log likelihood of about, or a negative minus log likelihood of about 216. And the minimum occurred at, I can't remember the value, was it 4.2 or something like that? And that's here, and that has a value of 202. And in fact, 216 minus 202, the log likelihood went down by 14, and that's significant, highly significant by either AIC or BIC. So here AIC and BIC tell us that adding nu as an MLE parameter is a good idea. And any amount of cross-validation or empirical tests would also tell us to do that.